So now let's talk about OLS. So we are going to talk about single equation with cross-sectional data, and we're going to talk about how to estimate by OLS, ordinary least square. Introduction. A general setup is based on the conditional density. The most general setups like this. We have a conditional density of the outcome variable y given x and coefficient beta. X is a 1 by k vector, and the beta is a k by 1 vector. So in 4a, I write I follow Aldrich and I write x as a raw vector. Some econometric textbooks may write x as a column vector and beta as a row vector. Here we write x as a row vector and beta as a column vector. And y is just a 1 by 1 scalar. It's also a random variable. So modern econometrics actually assumes y, x, or even beta to be random variable. So later when we talk about local treatment effect, when we talk about the instrumental variable, we're going to see some cases that even beta is a random variable. For now, let's just focus on the case that y and x are random variables and beta is not random variable. They are simply coefficients. In most cases, we are only interested in some feature of the conditional or joint distribution, and therefore we can study identification without fully specifying a distribution. Okay? For example, most of the econometrics focus on identifying parameters of the conditional mean, or sometimes maybe conditional median. Right. We don't necessarily need the whole distribution. Right? What is this guy? This is just the regression, right? The conditional mean. Right? Just like last time we talked about asymptotic, right? In general, we do not know the distribution of a random variable. That's why we rely on asymptotics. We rely on law of large number and central limit theorem, right? I mean, the similar logic applies here, right? In general, we won't know this guy. We won't know this conditional density, but we probably only interested in some aspect, like the conditional mean. So we may be able to estimate the conditional mean without knowing the whole distribution. And that's something we call identification. We're going to see that. Okay. So here just a quick example. So what is the regression? Right? We know the regression is the conditional mean of y given x, which is a function of x. Right? And but let's see the figure here, right? So this is y, this is x, and we have the conditional distribution of y given x, right? So for each x, let's say x equals x1, there is a distribution here. This is like f, the conditional distribution of y given x equals x1. Right, this is the conditional distribution of y given x equals x2, and etc. Right? And do we need to know the whole distribution? Well, not necessary. Not necessary, right? If we only care about the conditional mean, right, we may not need the whole distribution here. Okay? And like in this case, the conditional mean. In this case, the conditional mean is actually a linear function of x. Right? In general, of course, the conditional mean could be a nonlinear or complicated function of x. Okay? Yeah. So of course, of course, yeah. Okay. So, uh, we assume data are obtained as a random sample from the specified population. A random sample is a sequence of independently identically distributed random variable. Right, so this is a random sample, right, with sample size n, right, and we assume that there are IID, so all their mean EXI will be a constant, and all their variance will also be a constant, and all their distribution will be the same. Will be the same as well, right? Because they are all identical, right? And that's what a random sample means. So what is identification? What does identification means? So it means determine whether or not we can consistently estimate population parameters, the betas. It is closely related to model specification and mostly a population property. The reason is that if we assume random sampling, if we have a random sample, then there's actually no need to distinguish a, well, in terms of identification, there's no need to distinguish a sample or the population. We will see shortly. Right. So, given random sampling, issue of model specification and identification are purely population consideration. An estimator is a function of a random sample. So let theta hay be an estimator of for parameter theta. Then we call that weakly consistent if the probability limit of theta hay is theta. And we say theta hay is strongly consistent if theta hay converge almost surely to theta. In econometrics, when we say consistent, we actually mean weakly consistent. We mean the probability limit. Right? So the identification means whether we can create a estimator that create an estimator such that its probability limit is the true population parameters. Okay, so now let's talk about a linear model. So in the first half of the 4A, we are going to talk about only the linear model. So what does linear means here? Linear means that the parameter linearly enter a model. Okay. So we have a model like this. The parameter betas, they enter the model linearly. Right? So we don't have something like y equals beta 1 times beta 2x. Right? We only have beta 1 plus beta 2x. Right, so when we say a linear model, it means the parameters enter the model linearly, not the x enter the model linearly. Okay, and in fact, we can include any nonlinear function of x, such as like a log x, x squared, x cubic, and etc. In the linear model, the beta 0 here is called the intercept, and the rest of the parameters is called the slope. It's called the slope parameter, and they are in general a vector. Right. For now, we assume they are non-random. Okay. For notation convenience, from now on we will assume that the first component of the x vector is always 1. So beta 1 here will be the intercept. Okay? And we write the linear model as following, right? So y equals x beta plus u. And note that a model is written in terms of the population. Okay, this is our model, and it is written in terms of the population. Okay. And this is a random draw from a random sample, right? So when we add the I subscript, this actually means the sample. This is a random draw from a random sample. However, because if we have a random sample, and these two essentially are the same, it's just whether you add the I subscript or not, right? And that's why we say, well, when we talk about identification and talk about the model specification, like here, the model specification says it is a linear model. Model specification and identification is mainly a population issue, right? Because whether you write down a population or a sample, it's actually the same. So apparently we need to make some assumption, otherwise there's no way we can estimate beta using available data x and y, right? Right, that's identification means, right? Whether we can estimate beta consistently using observable data x and y, right? We don't observe u apparently. So we need to make some assumptions. The first assumption for the ordinary least square is zero correlation. The assumption assumes that E x prime u equals 0, right? A zero vector. This is also called orthogonality conditions. It assumes that x, the explanatory variable, are orthogonal to the error term u. Okay. And we can also write down, this condition is equivalent to assume that the mean of the error term is 0, and the covariance of xj and the error term are 0 for all j, for all the explanatory variable. So note that EU equals 0 is actually not a restrictive assumption. It is simply a normalization. Okay, we just assume that because the first component is 1, we assume that the first component is 1. So covariance 1, and the u becomes EU, right? And we need that to be 0. And it's actually a normalization. So we say all xj are exogenous if this condition holds. If the covariance between xj and the error term are 0, or more briefly, ex prime u equals 0. They are orthogonal. So a sufficient condition for the orthogonality condition is that the conditional mean of u given x is 0. If this is the case, then we can show that the conditional mean of y given x is x beta, right? Because y equals x beta plus mu, and EU given x is 0, then of course EY given x is just x beta. And this is something we call population regression. Right? The conditional mean, another name is the population regression, or simply the regression. Right? And in this case, in the linear model, with this condition, with this condition, then the population regression is a linear function of x. In general, so more generally, this may not be true, right? So if this is not true, this condition is not true, then the population regression may be a nonlinear function of x. Okay, and also note that this condition actually stronger than the exact. I mean, this condition here is a sufficient condition, so they are stronger than the orthogonality condition. The conditional mean of u given x is 0 means that u is uncorrelated with any function of x. So therefore, this is stronger than the orthogonality condition, right? That only assumes x and u are uncorrelated. But the conditional mean of u given x equals 0 means u is uncorrelated with any function of x. An even stronger condition is that u is independent of x. That implies any function of the error term are uncorrelated with any function of x, so that's even stronger. A second assumption is called no perfect collinearity. In matrix notation or in vector notation, that requires the rank of the covariance variance matrix equals k. This is also called the rank condition. That means this guy, E x prime x, needs to be full rank. And this guy essentially is the covariance variance matrix. Because we already include intercept in vector x, so the rank condition here implies that the population covariance variance matrix is full rank, which means the covariance variance matrix is invertible, right? So the inverse of this matrix exists, right? So that means this guy exists. This guy exists. Okay. So this condition is actually not very. So empirically, this condition is almost always hold. The rank condition means that you cannot have one variable is a linear combination of other variable. Right? For example, you cannot put say x1 is male and x2 is female. You cannot put both x1 and x2 in one regression. Right? Apparently, x1 is perfect collinear with x2, right? Because x1 equals 1 minus x2. So you cannot put both inside. If you put both x1 and x2 in the regression, in the vector, then the covariance variance matrix will not be full rank. However, empirically, that's not very important, because if you do that empirically, right, the software will automatically drop one variable for you, right? Especially in modern software like Stata, if you run a regression like that, it will just tell you, oh, there's perfect collinearity there, so one of the variable is dropped. Okay. But theoretically, this does means that you do need to have a full rank, and this also important means that I mean, it is kind of important in the sense that you cannot have duplicate information. Right? You cannot use duplicate information to generate your vector. Right? So your explanatory variable should not have perfectly duplicate information. Okay. So under the assumption 1 and assumption 2, with beta is identified, which means that we can write beta as a function of population moments in observable variables, in this case x and y. For because we can always get a random sample from observable variables, right? So we need to be able to write beta as a population moment of x and y, so we can draw a random sample on x and y and estimate that. So here are two examples, very simple examples for unidentified parameters. The first case is, well, x2 equals 2x1, so they are perfectly collinear. So apparently, if you plug in, we know y equals beta 1 plus 2 times beta 2x1 plus u, which means we can only identify beta star. We can only identify beta 1 plus 2 beta 2 together. We cannot separately identify beta 1 and beta 2. Right? And this is a case of perfect collinear. Another case is actually about the intercept and the error term. Suppose the mean of the error term is not 0, it's actually a constant c. Then if you take expectation, then the ey minus beta times ex will equals a plus c. What does that mean? That means, well, yes, we can estimate alpha, sorry, not a, is alpha plus c, but there's no way we can separately estimate c and alpha, right? We can only estimate alpha and c together, alpha plus c together. Okay, and that's why we say actually the mean of the error term is 0 is actually a normalization, right? Because we just normalize this c to be 0. There's no way we can separately identify the intercept term from the error terms. Okay. Let's see how to let's show why beta is identified under these two assumptions. So y equals x beta plus u. If we multiply x prime both sides, so x prime y equals x prime x beta plus x prime u, then we take the expectation. Then by OLS 1, this guy is 0. By OLS 2, the inverse of this guy exists. So we can just multiply both sides by the inverse. And that shows beta equals ex prime x inverse times ex prime y. And so both this guy and this guy are population moments of observable variables. So the derivation here has nothing to do with data and sample, right? We just deal with the population. And the ex prime x is a k by k covariance variance matrix in the population. Ex prime y is essentially a vector of population covariance. It's the covariance between x and y. In fact, in the scalar case, if there's just one dimension, we know that beta equals covariance xy over variance x. Right? Because covariance xy, if you just multiply x there, covariance xy equals covariance x beta, which is variance beta. And covariance x and alpha is 0, covariance x and u is also 0. So covariance xy equals variance x times beta, so beta is covariance xy over variance x. Right? And more generally, beta is this guy. Right? It's essentially the inverse of the covariance variance matrix times the population covariance between x and y.